Thank you very much. And thank you very much to the organizers for the invitation. As Jonathan said, my name is Nicholas Frattini. I'm a graduate student working with Michelle Deveray. And today I'm going to guide you, no promises on results, but I'm going to guide you toward a topological CNOT between two Kerr-Cat qubits. So I'll tell you a little bit more about what exactly that means in terms of Kerr-Cat qubit. But first, shout out, of course, to Shruti, who we collaborate very in depth with, and who you heard from before, and of course to Alex Grimm, who's now at the Scher Institute, and all the single qubit things that I will talk about will be as a result of his work directly. All right, so maybe first take an overview, step back in case everybody didn't get everything from Shruti's talk. I'll at least give you maybe a step back and say, how do we want to encode information? We'll talk about sort of the general story. We usually say something like, we'll have a physical qubit, and then we'll take them, we'll combine them together, put them in some sort of repetition code or surface code or whatever makes you happy. And we'll beat a logical error rate down with that. And we're also going to use these two-level systems as well to interact with this larger code and measure, for instance, stabilizers. And in particular, since this is the GKP anniversary conference, we are also going to use our two-level system Ancilla to measure stabilizers of our bosonic codes as well, like GKP. And you've already heard people cursing their Ancillas. And so hopefully we can ask the question, why are we so upset with our Ancillas so far? And the reason is because all of our physical qubits have errors. So we can decompose them into bit flips and phase flips, right? But we can ask the question if we can do a pre-step, if we like, and encode things before we move to the next level and create a protected qubit where we take, or noise bias, and we take one of these error channels, and if we ideally, we would completely suppress it. And it's been shown now, as Shruti just talked about quite extensively, that if we can use these now protected qubits as components in our repetition code or our surface code, we can increase the error thresholds. And also, similarly, if we replace our ancillas with these protected qubits, we can use them to do fault-tolerant now syndrome measurements, so that we can use that good coherence not to do some horrible back action on the state that we worked so hard to create inside our, say, for instance, our bosonic mode. So really, the summary of this story is that we want some protected qubit with one error suppressed. And we're going to use the two-legged cat qubit to do that, a little bosonic code in and of itself as the sort of building block to go from. So that sort of brings me to an outline of what I'm going to try to talk to you about today. In order to talk about how to do multiple things with a Kerr-Cat qubit, we need to start with one. So first, what is the Kerr-Cat qubit? And what are sort of the highlight of the things that we can do with it? So single qubit gates, readout, and the error protection capabilities that give you that protection that we so love. And of course, everything there was with Alex Grimm. And then I'm going to hopefully convince you and look at the theory of this topological CNOT between two Kerr-Cats, and hopefully convince you that indeed it's experimentally something that we can do and are excited to give it a shot. Okay, so from the beginning then, how do we go about stabilizing a cat qubit, right? We're going to try to store information in coherent states in an oscillator. So let's start with one. How would we go about fixing a coherent state in phase space? Well, the easiest thing to do is to turn on a drive on resonance, and in the rotating frame then of that drive, if I have some single photon loss, then I'll stabilize a coherent state inside my cavity with a given size, given by the ratio between epsilon and the loss rate. That's one way to make a coherent state, but there's also another way to make a coherent state, which is I start from vacuum and I drive detuned from my oscillator with some detuning delta. And if I do that, the ratio then between my drive strength and my detuning will also stabilize, will also leave me in a coherent state. So I will be in a coherent state. And actually there's a complete continuum between these two, and we can have both at the same time. And we get again to a coherent state with a slightly different phase or amplitude. Okay, but one coherent state doesn't make a qubit. So how do we go to two? Well, it was realized quite a while ago now and shown that we square everything, we make things better. So if we promise to add 2 photons at a time, that gives us this epsilon2 or this squeezing term. And if we promise only to take them away 2 at a time, then the balance between adding 2 and taking 2 away stabilizes for us now the Schrodinger cat states. So the superpositions of a plus alpha and a minus alpha state. And here I've shown for you the Wigner function of the even superposition with even photon number components, but also similarly the odd case. So, okay, this has been shown and people have been able to do that. But what about this remaining corner? So the remaining corner here is, well, we can take this Hamiltonian and we can do the same trick, we can square it. So if we square it, we have something which looks very familiar to people in superconducting circuits or optics, which is a Kerr nonlinearity. And again, we have the promise to add 2 photons at a time, or a squeezing drive. And it turns out that the balance between these two, again, will give us the cat states, 2 of them. And again, there is a continuum now between both of these. So if we'd like both of them, we can certainly have both. They help each other out, in fact. So, okay, maybe let's delve into this a little more. It's maybe a little opaque. Why does this in fact give us the cat states that we know and love and are expecting? So it's actually easy to see if you go ahead and factor that Hamiltonian, you can see sort of right away from this factorization that the coherent states of plus and minus alpha will be degenerate ground states of this Hamiltonian. Okay, they will at least be eigenstates. And as well as their superpositions. So you can see right away that we have a completely degenerate subspace here, which is spanned by these states. And again, the cat size is given by the ratio between the drive strength and the Kerr nonlinearity. And so if we can ask if we can make a qubit out of this, and to sort of understand that we can, it's useful to sort of picture this in a cut of phase space. We sort of have a double well where a coherent state will live on one side and the other, these will be our 2 states, but we don't have any tunnel splitting because as I showed you, these are already degenerate eigenstates. So they're completely degenerate here. And the reason I'm showing this to you is that all the other states are actually different in energy. And therefore we have this energy gap, which scales as the size alpha squared. And that gap allows us to focus, just like we would normally do in a transmon, on the 2 degenerate levels and define a block sphere in which we hope to stay. Again, a question on conventions here. I'm going to stay even cat on the top and odd cat on the bottom, and alpha and minus alpha along the x-axis of the block sphere. But I'll try my best to give you intuition in terms of coherent states versus cat states, so you don't have to remember the convention that and from here, we can already sort of see the protection that this qubit can have. These 2 coherent states are far apart in phase space. So any noise that tends to jiggle them around or tries to move them, it's very difficult for the environment to take one to the other. And that is what actually gives us an exponential suppression of this bit flip, or of what I've called a phase flip rate here. So alpha to another alpha. And what we pay for that is the overhead, which is linear now, in the fact that we're using, on an average, n bar more photons to encode our oscillator. So the goal is to gain exponentially, but lose in overhead linearly. Okay, and this dependence was actually shown recently in the dissipative case by Zaki's group very, very nicely. So we really can indeed count on this protection. So in lab now, how do we actually make this device? Well, Shruti already alluded to it. We'll take a low anharmonicity snail transmon. What does that mean? Well, it's a transmon, a 3D transmon that you know and love, 2 pads with a capacitor, except now the Josephson junction has been replaced with this snail element, which looks kind of like a flux qubit, actually. And we're gonna use a non-zero magnetic flux. And the only thing you need to know about the snail is that its 4th order nonlinearity, again, gives us the Kerr. And it also has a 3rd order nonlinearity, which when we drive it twice to frequency, we can activate to get this squeezing term, or this 2-photon drive. So that in and of itself gives us both components of this Hamiltonian that we need. So really, I want to emphasize that all of the action is happening inside the most nonlinear mode in this system. There is no other ancilla here. This is it. It is all in the one transmon-like mode. And the copper cavity you see is purely for readout. And yeah, which means that the main loss channels that we have to contend with are the photon loss in this thing due to the fact that it participates a little bit in the copper and some flux noise as well. So that's the physical implementation. We can generate this Hamiltonian, and we're also going to want to be able to do gates. So we're going to we can apply those gates, for instance, by driving on resonance with the oscillator. And what that will do for us is if we drive on resonance, the single photon drive will lift the degeneracy between plus and minus alpha. If you like the double well picture, you're sort of tilting it. And since we have an energy difference between them, we can now do Rabi oscillations around the purple circle of this block sphere. So between the different cat states. And if you like the fringes picture, we're pushing the fringes along and moving between the different cat states. However, this single photon drive is unable to take population from one coherent state to the other. If coherent states are eigenstates of A, so they should leave it unchanged. And that's true. We can only Rabi around the x-axis of this block sphere, around the purple circle. So since we can only go that direction and we have continuous control over that, and we can do it pretty fast. We can do it in 24 nanoseconds with pretty high fidelity. And the limit on that is really only that effective anharmonicity, or that energy gap that we talked about earlier. To get everywhere on the block sphere now, we only need one more gate. And that's a gate that is actually a discrete gate now. We're going to go outside the block sphere to do this gate. We turn the squeezing off, let Kerr act for a certain amount of time related to 1 over Kerr, which for us in this case was 38 nanoseconds. And that will take a coherent state and refocus it to a parityless cat state. So we're sort of allowing the Kerr evolution to act and then turning it back off by squeezing and stabilizing again this location. So we can do that quickly, and it allows us to move wherever we want on the block sphere. Okay, single qubit gates are good. What about readout? So readout we can actually do, and we're able to achieve in a single shot and quantum non-demolition fashion. Just one more drive to the system allows us to create a conditional displacement Hamiltonian between our readout cavity, now this C, and now sigma x. So if you like, it's easier to see in the histogram. If we prepare plus alpha, then what we measure is the displace to the right. And if we prepare minus alpha, then what we measure is a displace to the left. So we have readout, if you like, on plus or minus alpha along the block sphere here. So if we can do gates and we can do prep and we can do readout, that means we can measure coherence. And so to show you that these cat states do indeed live a long time, we first do some operations to prepare either the plus alpha or minus alpha state, wait a variable amount of time, and then turn on this cat quadrature readout. And what we are able to see is single exponential decay of that coherence with a time scale of 105 microseconds, which is pretty cool because the 105 microseconds should be compared to the T2 Ramsey that we started with, which was 2.6 microseconds, or the T1 of our transmon originally, which was 15 microseconds. Not the state of the art for both of those numbers, but those were what we had, and we were able to make better. We can do similar gate and preparation sequences to measure the lifetime of the cat states, but overall, you can see that what we've done is taken a not the world's best transmon that's susceptible to some flux noise and make it much, much better. And more importantly, we've been able to do this in such a way where we've made one axis very good and well protected, and the other axis is still long enough that we can still do our gates with high fidelity in this amount of time. So that's sort of a grand summary of our single qubit results, gates, readout, and coherence times. And so we're done. No, not really. Of course, a single qubit does not make a quantum computer, and so we need more, right? We need to go to more. And what Shruti already showed you in the grand vision of more is her stylized surface code of cats, which I'm showing over here. And she showed you that you were able to increase the error threshold, with the caveat that only if all the gates that you do preserve this protection, preserve this bias that we already worked so hard to create. Now we already have that for the single qubit gates. And the question is, what about 2 qubit gates? And the 2 qubit gate that we need most for the surface code is the CNOT. So quick reminder, based on the state of the target qubit, we're going to flip the other qubit. So depending on which coherent state, we want to flip the other coherent state. And in fact, there's a no-go theorem here, which was first suggested and later proved, that it's impossible for a set of 2-level systems to preserve the protection during the CNOT. So you can't actually, even though the unitary itself is fine, any Hamiltonian with 2-level systems that implements this unitary will not be able to preserve this error protection that we so need. And the name of the game here is that we can bypass this no-go theorem with cats. And I want to sort of give you an intuition of how we're able to do that. And really it's because we have very, very many states in our oscillator. We have the infinite Hilbert space, and we are able to use the topology of phase space to do that. So to show you and build up to that CNOT, I first want to take it back and do a single qubit gate now based on the same mechanism. And it's going to use that topology of phase space and do an exchange to do this operation. So now a single qubit discrete gate. And the property that we're going to use is that the cat axis, whether it's horizontal or vertical or what have you, depends on the phase of the 2-photon drive tone that we're applying. So the cat axis is locked to that phase. And so if we adiabatically now roll that phase, we will go through different but completely equivalent cat codes, if you like. We do a code deformation. And this deformation, right, since we stay in the cats, if you like, we can show it to you in math. We have the even cat on top and the odd cat on the bottom. Rotate all the way around. And what you see in the math is that at the end of this rotation is we get the even cat back with a plus sign, but the odd cat with a minus sign. And that minus sign is completely topological. It's by the fact that we did this rotation. It doesn't depend on the time that it took. It doesn't depend on the path that we took. Say we had some noise that jiggled us along the way. It only depends on the fact that we did this exchange process, the fact that we did this rotation. And it's that robustness that is going to give us the protection. So maybe you don't believe me that this is actually doing the gate that I promised, this exchange, but here you can show it for each of the states. I like little videos and it helps me visualize it. So the coherent state switches around. The Y states, you can see change the order of their fringes, and the cat states, then the even and odd come back to themselves. And really now, the key here is that the error protection during this gate is exactly the same as it was when you weren't doing the gate. So if your error protection was good before the gate, during the gate, it's exactly the same. The coherent states stay just as far apart. We're in exactly equivalent codes. And so this is just purely code deformation.
So now 5 minutes till questions, Nick.
5 minutes, perfect, thank you. So now we've got the single qubit gate. So the question is, how do we do it? How do we do it on a 2 qubit gate? What we need to do is do this topological gate dependent on another cat qubit. And since I can't now draw for you all the connections in 4D space, what I'm going to do is math instead. So the CNOT gate, we need to exchange in cat A dependent on cat B. So here is a Hamiltonian. Shruti gives it to you and says, make it. And now you need to step back and ask, does it actually do what you think it does? So maybe one term at a time, you stabilize cat B. This is just the Hamiltonian that we had before. And then the next term is supposed to be the stabilization for cat A. And we can see that these terms that I've sort of colored will be either 1 or 0, depending on if cat B is in plus beta or minus beta. So let's say cat B is in a state in which it is minus beta, then these terms will be 0, and these terms will be 1, in which case we'll just have an alpha, which is rotating now, some phase phi, which we're going to change from 0 to pi. So that will be the case where we do that rotation that I was showing you before. And if it's in the other state, then we'll just have a standard stabilization of alpha squared. So that sort of gives you the big picture. But the question is, can we experimentally implement it? What do we actually need to do? So we can expand this Hamiltonian, and we can sort of see the types of terms that we need. So the first is, again, the stabilization of cat B, which we already know how to do by driving at twice B's frequency. We have the Kerr in cat A, which we can get by just having, which comes for free, if you like, with our implementation. You have the 2-photon drive on cat A, which is a stabilization. Again, we already know how to do that. Let's drive it to omega A. And now we have the interesting term, the interaction, which is a 2-photon drive, which depends on B. And it turns out we can implement this with only one more drive at 2 omega A minus omega B. So what we're going to do for this gate is we roll phi from 0 to pi, is we're going to have a 2-photon stabilization on. We're going to turn it off as we turn on this interaction. And then we're going to turn the interaction off as we turn stabilization back. And if you allow me to claim that there's no leakage during this, I can show you that this factors into a really nice form, which is that you can really see that you have a 2-photon drive whose phase is depending on the plus or minus beta in cat B. So that's good. That means we can design an experimental implementation. All we need is that 2-photon drive dependent on cat B. And that requires 4-wave mixing and 1 drive. 4-wave mixing now between 2 Snellmans, which if we have a capacitive coupling between them, is sort of an architecture that looks like this. We have Snellman, readout resonator for cell filter, and a second down here at the bottom on the second chip. Capacitive coupling between them gives us a cross-Kerr interaction. If we drive that, we can generate this term, and we should be able to get all of the things that we desire for the gate. So we have gone ahead and made this and cooled it down, and we have magnetic flux, and we are excited to give you some results, hopefully soon. So hopefully I have convinced you that the Kerr-Cat is indeed a noise biased qubit, that we have fast, high fidelity gates in the single qubit land. And actually it supports this topological CNOT gate that we can defeat this no-go theorem. So thank you very much.
Well, thank you, Nick, for that great talk and ending with plenty of time for questions. Nothing is in the chat yet, but again, don't be shy. Please ask something. While we're waiting for that though, a question did occur to me when you were showing that beautiful Hamiltonian for your CNOT gate. Oh yeah. So actually maybe I'll hold off on my question because Arne is asking something that's probably more intelligent. He wants to know if you can comment on the readout fidelity of biased cats in current experiments and maybe speculate or guesstimate what it could be in future improved versions.
Yeah, so I would say the general theme of our first experiment here was that we needed both a decent transmon to not make our lives too difficult and try to make the best cat qubit we could. And now that we've done it once, we can make all of our transmon things worse. And hopefully as we do that, we'll make all of our cat things better. So that's a long way of saying that in the last experiment, our transmon readout and our Kerr-Cat readout, if you like, were of equal fidelity, which is pretty cool. And so now we've turned down our ability to do transmon readout, and the fidelity should, I mean, get better. We've already seen more separated blobs in this sample than we had before. I see no reason why it shouldn't get better. Larger cats also make the readout better. Yeah.
Excellent. Yeah. Joachim is wondering how fast you expect the gate to be, the CNOT gate.
So it turns out you can actually go pretty fast because you have as you rotate, if you like, you have the energy separation, which is the gap to the next excited states. So in terms of numbers, I think we're looking at the sort of 100 nanosecond level even for the first go of the experiment. But I'll let you know if that fails, I guess. But it seems like we should be able to do it at a reasonable clip because our gap is something like 50 to 100 megahertz. So we can, yeah.
Nice. All right, well, I guess I can ask my question then. And my question had to do with the kind of approximations you're always doing when you're building these Hamiltonians. And you pointed to this beta minus B term that's basically like a projector onto the beta minus coherent state, I think.
Yes.
But then you have the kind of annoying problem that in the conjugate part, there's this like beta minus B dagger, which isn't quite a projector.
Exactly.
Do you know, like, the back of the envelope, like how much like air you get from that compared to your other sources of air in the experiment?
So what I guess what I can say is that I'm not worrying about it, which is the statement that we have simulated it with I've actually ignored some terms in the initial Hamiltonian when I gave it to you. And even with ignoring those terms, we can reduce it down to one drive. And in simulation, at least for reasonable parameters, get 99% fidelities in reasonable times for cats that are of sizes that we can make. So maybe, down the line, we'll need to worry about that sort of approximation. But honestly, like that approximation just gets better and better as you learn to make bigger and better cats.
Right, it would be bad for really tiny cats, but
bad for tiny cats.
Yeah. Let's see. Is there any more?
I think Shriti had one in the chat. How hard it would be to make the lifetime 100 microseconds, and sort of what's the deal? So the main limitation on the Snellman lifetime itself is the copper of the surrounding readout cavity, which is by no means fundamental. Here, again, there's some copper to try to get magnetic flux through. So we're sort of working on engineering ways of getting DC flux through. This is sort of a easy way of doing it that at least so far I've already gotten 25 or 30 microseconds here, up from our 15 from before, which is not 100, which you asked for, but many smarter people than me can work on, have ways of simulating that better and making it happen, I think.
Excellent. Let's see. We might have time for one more quick question. But if not, yeah.
No, it's okay. I can ask on Slack.
No, go for it.
Oh, so I was going to ask, like, do you plan to do like full-fledged tomography when you make the CNOT gate, or is it going to be something like a benchmarking thing, or?
I think it's too early for me to commit to something like that. I will say we will do the best we can to do. I think we want to be convinced that we're doing it. So we'll need to do some form of full tomography, I think. But I'm not. I have an open mind in that respect.
Excellent. Always good to keep our minds open. Well, thanks again, Nick, for a very exciting guiding us towards the CNOT gate. And so now it's